Hi, welcome to video 1 for lesson 3.2 on the exponential distribution. Suppose that y is a random variable that follows a Poisson distribution. We use the parameter lambda to be the mean number of events per unit of time or space. And y, remember, was the number of events that occur in a single unit of time or space. And the probability mass function, f of y, was equal to lambda to the y times e to the minus lambda divided by y factorial for the non-negative integers 0, 1, 2, and so on. What if instead of the number of events occurring in a unit of time, we're interested in the time until an event occurs? If we let x equal the time until the first event occurs in this Poisson process, we know that that time has to be greater than or equal to 0. If we call the mean time until an event occurs mu, the expected value of x, we give that the notation theta. Then the probability density function, little f of x, is equal to 1 over theta times e to the minus x over theta for values of x greater than or equal to 0. And this is what's called an exponential distribution. The mean of the exponential distribution we called theta, and that's equal to 1 over the lambda from our Poisson process. And the variance, sigma squared, is equal to theta squared. And so that's equal to 1 over lambda from the Poisson process squared. So I've kind of given away the punchline here, but what I'd like to do now is show us why these formulas are correct. So remember, y is our Poisson random variable with parameter lambda. X is the waiting time till the first event occurs. So the cumulative distribution function, big F of x, is the probability that the waiting time is less than or equal to x. And it's going to be 1 minus the probability that no events occur in the interval from 0 to x. If we treat x as the unit interval in our Poisson process, then the mean number of events that occur per unit interval is going to be lambda times x. So our cumulative distribution function, big F of x, is actually equal to 1 minus lambda x raised to the 0 power e to the minus lambda x over 0 factorial using our Poisson PMF. And we can simplify this to show that big F of x is equal to 1 minus e to the minus lambda x for values of x that are greater than or equal to 0. And it's going to be 0 otherwise when x is less than 0. Now to find the probability distribution function, our PDF, little f of x, we can take the first derivative of our cumulative distribution function. And when we do this, we get that our PDF is lambda e to the minus lambda x. Now if we let theta equal 1 over lambda, we can rewrite this in terms of the parameter lambda as 1 over theta e to the minus x over theta for x greater than or equal to 0. And that was our probability density function for our exponential that we saw earlier. And we can use the moment generating function to find the mean and variance for the exponential distribution. Remember that our moment generating function, m of t, is equal to the expected value of e to the tx, which in our case, it means that we're going to integrate over the support from 0 to infinity, e to the tx times f of x, so 1 over theta e to the minus x over theta dx. Because we have an integral going to infinity, we're going to take the limit as b approaches infinity of the integral from 0 to b of 1 over theta e to the minus 1 minus theta t times x over theta dx. And I just kind of move that stuff around to make it easier to do our integration. And I can work through this problem and show that the moment generating function m of t is equal to 1 over 1 minus theta t, or written differently is 1 minus theta t to the minus 1 power. That's the general form for moment generating function for an exponential distribution, either of those. Now, if I want to use the moment generating function to find the mean and the variance, I need to start with my moment generating function, 1 minus theta t to the minus 1 power. I'm going to need the first derivative and the second derivative. Remember, my mean is the first derivative evaluated at 0, and this gives me my theta. And the variance is going to be my second derivative evaluated at 0 minus the mean squared, which was our theta squared. This gives me 2 theta squared times 1 minus 0 cubed minus theta squared, which gives me theta squared. So I just showed that the formula is correct for the mean and the variance. Before I finish the video, I'd like to work through an example. So during the dinner hour, orders are received at a pizza shop according to a Poisson process on the average of 3 calls every 5 minutes. So let X be the waiting time until the first order is placed. We want to know what is the PDF of X, what are the mean and variance of X, and then what is the probability that the first call will be received in less than 90 seconds. So here, I know that X follows an exponential distribution because it's the waiting time until the first event in a Poisson process. I know that my theta is going to be 1 over lambda from my Poisson process. Lambda is 3 calls every 5 minutes, so 3/5, which gives me a theta of 5/3. So if I write my PDF, f of x equals 1 over theta e to the minus x over theta, that gives me 3/5 times e to the minus 3x over 5. Here's my PDF. The mean of my distribution is going to be theta, which we said was 5/3. The variance, sigma squared, is equal to theta squared. So 5/3 squared gives me 25 over 9. And now if I want to find the probability that the first call will be received in less than 90 seconds, 90 seconds is 1.5 minutes. I know that my cumulative distribution function is 1 minus e to the minus 1 over theta x. I plug in my value for 1 over theta and my value x of 1.5, and this gives me my answer, 0.5934. And that's how we can work with the exponential. So I hope this video has been helpful for you. If you have any questions, feel free to ask. Coming in our next video, we'll be looking at the distribution of the time until the nth event occurs instead of the first event, any nth event. And this is going to follow what's called a gamma distribution, and that's what we'll see in our next video. Thanks, have a good day.